tools. We're going to move on and look at our Cray debugging and support tools. And the debugging and support tools do include a suite of tools. We've mentioned a few of them. The main one that we're going to focus on is Gdb4hpc. So that's where we're going to spend our time for the balance of this class, and we do have a hands-on exercise for this. There is a number of other tools in the suites, Valgrind for HPC and sanitizers for HPC are HPE unique offerings in both cases, and similarly with Gdb4hpc, they are based on publicly available tools. And in fact, if I remember Helen's introductory slides, there is an upcoming training available to NERSC users on both sanitizers and Valgrind. So I don't know. I might try to sit in on that training because I am also a NERSC user. But I believe those trainings, from the title at least, appear to be on the basic, the publicly available versions of Valgrind and sanitizers. Valgrind, by the way, from what I was told, was the contributors to that code are from somewhere in Scandinavia, Northern Europe. So it's kind of got this Viking Norse pronunciation, Valgrind. You could be forgiven for calling it Valgrind, but I personally have been corrected by those in the know. So I'm giving you that pro tip there. So, but yeah, if you know how to use the standard tools, Valgrind does checks for memory leaks and other types of things. They're both sort of batch debuggers, and sanitizers can, again, look at how your code is accessing memory regions. And I have not used either of them in a meaningful way. So we're going to save you the time and not present on them here. But once you know how to use the standard tools, you might try using the 4HPC versions that are unique from Cray, or from Cray/HPE. And what you'll get is, while the standard tool works and provides output for a serialized program, the 4HPC variations of the program are custom built to work best for parallel programs, right? So that's kind of the value that we're adding. And again, there was some documentation on it, but once you know how to use the basic tool, then you can come over and try the Cray tool, and might save you some time, might be useful for you. Here we're going to focus on Gdb4hpc. And again, this is our parallel debugger based on the GNU debugger. So if you've never used the GNU debugger, there is documentation out there for it, and it is useful. My own, albeit limited, programming experience, of course, I've done some debugging, but when I first came into programming, I was using graphical APIs, right? So where you see your code and then you run your debugging through the code, through the graphical debugger, and you kind of watch it run. And my first time using GDB was a bit of a wake-up call, because it's a command line debugger. So you don't have that nice pretty window that shows you where you are in your code, and you don't get to hover over things and have things show up. So you might just say, oh, well, that trainer doesn't know what he's talking about because he's hasn't done a lot of real debugging. And I've used GNU debugger now, but that was just my initial reaction. So if you've never used a command line debugger, I guess you're not alone, and you can still debug if you haven't used a command line debugger. We're going to try to help you with that right now. So you can use Gdb4hpc with all of the compilers that are available on Perlmutter, right? So, well, at least all of these. I guess LLVM is a compiler that NERSC staff have provided in addition to this list. I don't know that it wouldn't work, but we haven't tested it with that. So but certainly Cray compiler, GNU compiler, NVIDIA compiler, and the rest of them, you should be able to use our Gdb4hpc with any of those. It doesn't. It works with all workload managers. You don't care. It definitely works with Slurm, and that's the one that we use at Perlmutter, so that's fine. But it works with the GNU debugger. So there's some pretty good documentation available from on our HPE documentation site, so you can check that out. But we'll kind of walk you through the basics here in this demonstration. So as with a lot of things, I tend to default to the Cray programming environment and the Cray compiler. That is a bias of mine, and you know, we just go with it. But again, you can do this with any of the supported compilers. In these examples, when these, by the way, the hands-on examples that you're going to be doing in the lab are the same examples that I'm demonstrating in these in this presentation, so that you know what you like to do. What I found is for the Cray compiler, I needed to load the CUDA toolkit 12.4, which is available at Perlmutter. Some of the other compilers can use the default CUDA toolkit, and so that's, you know, if you want to use Cray, you have to go to 12.4. If you use GNU, you can probably get by with the 12.2, which is default. So there's that. Because we are building a CUDA code, we need to use NVCC. That's just how we build CUDA codes. And so NVCC -G is the debugging flag. And so that's fairly universal. We see that on our standard compiler as well. -G tells us to debug the GPU stuff, right? And so this is for CPUs, this is for GPUs, right? Now, when you debug, you want to limit the compiler optimizations. And the reason for that might be a little bit counterintuitive, but especially in the case where sometimes the optimizations are introducing the bug, but that's a slightly more advanced topic. But if you remember, my friend on the compiler development team, I'll just call him Gary, he makes the statement that his job is to rearrange your code so that you won't recognize it. And he's very good at that job, and he gets very good performance. But if your code has something where it's giving you a bug, it's giving you the wrong result in a particular scenario, and you are going through your code line by line in a debugger, then it's a little bit less helpful if your code has been rearranged so that you won't recognize it, right? So for that reason, we generally recommend debugging without optimization enabled, right? And in fact, the -G will disable optimization inherently, right? So that's on the GPU specific debugging, you have to have that disabled. Another just kind of general tip with debugging, especially if you're running your code optimized, which of course you would want to do for good performance, but if your results are having problems, lowering your general optimization, this -O flag, so 0 is lower, 2 or 3 are higher levels of optimization. When you lower that optimization, you could possibly get a different result. If the result at no optimization is accurate, and your result with higher optimization is wrong, then what you may have done is you may have discovered a bug in the optimization, or you may have identified that your program is not very tolerant to optimization, right? This is kind of a slippery slope of marketing versus, you know, whose fault is it and all that. But at least it's useful to understand that optimization and debugging are often at odds. So just understanding how that relationship plays out is useful to be aware of. Again, NVCC, when it runs, it sometimes needs to do some just regular C and C++ compiling. So we provide this CC bin. So basically, what is the compiler binary? And in that case, we want to use the Cray compiler driver. which again points to any of the compilers based on the modules, right? And then NVCC needs to be told which GPU architecture to build for. So this is the string that you want to use at Perlmutter. This refers to that A100 GPU. So specify that. Here we're specifying our CUDA code, and we're specifying an object file that we want to write out. And pretty straightforward. This simple MPI is an MPI CUDA application, again, that we got from NVIDIA. It's one of their CUDA samples. And so that's what we're using for this demo and this presentation. Once we've compiled our CUDA, then we need to link and build it, so for final execution. So I'm using the Cray compiler driver for C++. I'm specifying, again, we want debugging flags and we don't want to optimize. And then I'm saying that we want to do an intermediate step. We're going to compile our C++, our main program, right? And we're going to generate an object file there. And then finally, we're going to link those together with this compiler driver does both a compile and a link, right? So in this case, I'm calling it to compile, and here I'm calling it to link, right? And very simple programs, you don't need to call it twice. In this case, we are doing that for simplicity or illustrative purposes. I'm not sure which. This is what I was told to do, and it seems to work. So then, in general, when you are debugging, this is an interactive debugger. It is possible to kind of do a batch debug. So effectively, you kind of pre-specify the commands you want to run through the debugger and run them all as a batch job and not interactive. There can be some utility to that, especially with complicated things. There's a high setup cost, and you don't necessarily know when it's going to run. I have not used the debugger in that capacity. The capability absolutely exists. That's not what I've done. So I typically run the debugger in interactive mode, and which we'll walk you through doing in this next slides. Usually, this is my approach. Everyone's entitled to their own view. Usually, I think that you want to understand what your program does before you try to debug it. I mean, right? And further, not just understand what it does, but see whether it has a bug. So, I mean, it's sort of a joke, but I'm not kidding, right? You want to be able to run your application, and if it won't run at all, if it has like it crashes on load up, that's a separate issue, and we actually have a debug or a separate tool in the suite called ATP, and you can check into that. We've previously provided some training on ATP, that abnormal termination program, I think is what it stands for. So you can check that out. It's in the Cray debugger suite. So assuming your program runs, you want to run it, you want to know how you would run it and at scale, so that you can see how to run it through the debugger. So in this case, we have a simple script that's going to run our application. We're going to run 4 MPI ranks. We're running on a single node. Here we're specifying 32 CPUs per node. And again, this is logical CPUs. So your 64-core processor has 128 logical CPUs because it counts the hyperthreads. And so if you're running on one of the GPU nodes, which we are with the constraint GPU, and we're running 4 ranks on one node, we basically take those 128 logical threads, we divide them evenly and say, okay, they're 128 divided by 4 is 32. Each of our ranks is going to have 32 cores. And again, that's logical cores. So really, they're only going to get 16 cores. But that helps Slurm to place your job the way you want, right? We're also specifying that this job is using 4 GPUs. And in this case, we're using one GPU node, which has 4 GPUs. if you scrutinize the code, you might recognize, and I'll be honest, I don't know for sure, it might not actually utilize all 4 GPUs. But in this case, since we're consuming the whole node, we're going to just say that we want all the GPUs on the node. And at least that's going to tell Slurm not to share it. Also, our quality of service is regular, not shared. That's another pretty good indicator. Being overly explicit with Slurm is a good thing, right? So we know how our program runs. We are able to run it, and that's an important thing to do. All right. So as I mentioned, you can debug in batch. That is sort of, in my opinion, an advanced topic. And so we're going to start a little bit more basic with some interactive debugging. And so in order to do interactive debugging, we need to create an interactive allocation. If you've not done that before, that basically means that you are, it's like submitting a job, but instead you're submitting a request for resources or allocation, if you like. And you're saying, I need some number of nodes, for me to log into and use interactively. And it's pretty cool. So the general approach to doing this is you need to provide an account because you are consuming resources and someone's got to pay for that. You have constraints, so GPU, CPU are the 2 options at Perlmutter. You need to specify the number of nodes, and you need to specify a quality of service. At Perlmutter, at NERSC rather, they have set up a quality of service called interactive that you can use, and it assumes that everything within this QoS is going to be interactive or basically using salloc. So you can read more about that. A note on that, there is also a quality of service called debug. And it is possible to run interactive jobs in the debug queue, but that is maybe not always what you want to do. Interactive is probably better for salloc type stuff. And so just again, there's good documentation. In fact, down here, there's good documentation that explains a little bit more about these quality of services that NERSC staff have set up. Of course, when we're using the resources, we absolutely need to put a time box around it, right? So, and this is, when you run your batch job, you also need to specify a time box. When your batch job finishes, your job ends. In this case, with an interactive allocation, when your time runs out, your job ends. And it doesn't really matter if you're finished, your job will end. So on the good side, like you stop paying for it. And on the bad side, you might not be done. So kind of plan accordingly, right? Utilize or allocate time that you need. And there are limits, right? So you can't just say 2 or 3 days. They seem, from my glancing, somewhat generous, right? So again, check the policies here to see what kind of timing is available when you
just quickly add
Thank you.
interactive allows you to up to 4 hours, but there are a number of up to 64 nodes, and it's shared among your members in the same project. While
Thank you.
debug allows up to 4 hours, but only debug allow up to many more bigger jobs, but up to only 30 minutes. So
Sure.
interactive is 30 minutes, and it's actually quicker to get nodes than debug usually.
Thank you,
But
Helen.
smaller jobs, and on the other hand, debug is bigger jobs, 30 minutes.
Good. And both of those, they're documented here, and people can refer to those and should. So
Yes.
In my experience, I use debug because I was debugging, and 30 minutes was plenty for me. But it is in the cases I ran through this a handful of times on Perlmutter getting set up, and in both times, or all the times rather, I was impressed how quickly my allocation was granted. It might have been luck, but I think it's also they fully recognize that interactive use and debugging, while not necessarily the same thing, they're both necessary. And so there is a portion of the system that's kind of carved up set for that purpose.
Yeah.
And yeah.
So the limitation we set are for the purpose of quick turnaround for people doing interactive debugging.
Right. You wouldn't want to do an
That's
salloc and then, oh, well, it's ready at 3 a.m. you know, although you could, if, it's 3 a.m. for somebody everywhere. Okay. Thank you, Helen, again. Just another note, if you haven't done this before, the way it's set up at Perlmutter and the way we typically set things up at Cray, although it's not universally true with Slurm, when you do an salloc and it's granted, you will be moved to the first node of your allocation. And so you can, I think it's something like an SSH, although it's automated, so I don't know exactly how you get moved there. But so this is a contiguous line from my terminal, right? I did an salloc, I got some output, and then my prompt changed, and now I am no longer on the login node. I am on NID 1073. So that's the behavior at Perlmutter, and that is a common behavior, but not universal. So something to be aware of. When you do this, your environment comes with you as you just as if you when you run a batch job, the environment goes with your batch job, right? That's the behavior that Slurm takes care of. So if you haven't already loaded modules, you can do that here. And if you have already loaded them, they should be as you set up. In this example, I had previously built my application and I had loaded some modules for that purpose, but I hadn't loaded Gdb4hpc. So I'm loading that here. And then I'm going into the interactive debugger just by typing Gdb4hpc as the executable. We can see some output gives us the version and a couple other things. And then our prompt will change once again. And this indicates that we are now in the interactive debugger. Okay, so when you are trying to launch your application in the interactive debugger, you need to understand how to launch your application at all, right? Because if you can't launch your application, it's going to be really tricky to run it in the interactive debugger. So worth noting, and also from an interactive allocation, you can just use srun, right? Because you've already got the nodes assigned to you. You don't need to go to the scheduler and get time using like we typically would with sbatch. You can just run srun, and all of the parameters that you set up with your allocation will be inherited by your srun, because you're inside the allocation. So here I'm specifying a number of MPI ranks. In this case, I'm specifying that I want to run on 2 nodes, again, with 32 cores, logical cores per rank, and that my job is using a total of 8 GPUs. If I specified different values, like I could run smaller than my allocation here, obviously I can't run larger than my allocation, right? So this is some common launch arguments that we use with Slurm at Perlmutter. There are quite a few more. So CPU binding, GPU binding, things of that nature are things that you could include in your launch arguments, right? So sometimes this could be quite large, but whatever you're doing to run the job natively, you need to understand that so that you can run it in the debugger, right? Of course, we need the path to our application. And it's not, in this particular case, the application doesn't take arguments, but if we had arguments, we would know that as well. So typically you might have additional arguments or something, that you pass on the command line to call your application. And so those, we need to note that as well, although they're not applicable for this simple program. So here I've run the application. We see it's doing a square root. Great, that's nice. And now we're going to go debug it because maybe this value is wrong. For the record, this particular application, I'm not aware of a bug. Doesn't mean there isn't one. I'm just not. I selected an application that's doing some GPU work to give you an opportunity to test out debugging with the GPUs. So we're going to it's more of a navigation playtime than actually trying to debug this application, but that's fine too. And I tell my kids, everyone everywhere can always do better, right? So we have an application. I didn't write it. Some smart person did. I don't know very much about it, but I know because I believe that we can always do better, right? So do with that what you will. Anyway, we're going to load Gdb4hpc. And then the command is to launch. Now, when you launch, you specify a number of MPI ranks, and you also specify kind of a handle or some kind of hook that you will refer to this process as. In this case, I was oversimplifying it, and I said, all right, my program is called Simple MPI. I'm going to have Simple MPI be my name as well. If you don't like typing, there's nothing wrong with the letter A. And if A is already used up, there's nothing wrong with the letter B, and so on and so forth, right? In fact, you can you can launch multiple applications with Gdb4hpc in the same session and do some parallel debugging of multiple applications, in which case, keeping track of which is A and which is B, or giving them a more descriptive name is, a useful thing. That's kind of a next level practice. I don't do that, haven't done that, but you can do, right? And so we have this comparative debugging technology that this tool supports. So once you specify your ranks, and the ranks are in curly brackets, you can see there next to your label, then you specify your launcher arguments, which are exactly the same as what you used, except for the minus lowercase n. And then if you are doing debugging of a GPU application, minus GPU is a flag that Gdb4hpc needs to tell the tool that this particular application we're debugging has GPU codes, and it works with both NVIDIA GPUs and AMD GPUs. And so in both cases, we've leveraged vendor tools, GPU vendor tools for debugging those particular portions of the code, right? So we've done a lot with CPUs, we've done a lot with debuggers, but NVIDIA is the place to go if you're working with NVIDIA GPUs. AMD is the place to go if you're working with AMD GPUs. And in both cases, we just leverage the respective tools and incorporate it into Gdb4hpc. So then that's how you turn that on right there. You have a path here, but if you had, again, additional arguments, you would pass that with minus args, and then in quotes, whatever those arguments might be. If you took some input, you provide that there. When you run this application, it will give you some output, and it depending on how long it takes to start, you will get some number of lines here. At the end, it will say, here is your label that you've created, and you have 8, well, in this case, 8, so numbered 0 to 7 ranks. All of the ranks are at the initial breakpoint. The initial breakpoint is set for you basically at the first executable line of your main program. So it did that for us, which is at line 63 in our C++ program. And we have an empty prompt, right? So now it's time to debug on the command line. Again, if you're new to this, have fun, it's good. So what can I do? Well, help. Help is a good start. So if you type help, it will tell you what you can do, and it'll give you a list of other commands. And if you don't feel like you understand those, you can type help followed by a command, and it will give you usage, particularly on that command, right? So in a sense, help is at your fingertips, right? You can always just kind of figure things out. The first thing I like to do, because when I'm interactive debugging, I need to see the code. I haven't committed it to memory. I list, right? So list is a command that will look at where in the program execution you are, and it will print out basically the next 10 lines of source. Now, with a parallel program, all of your lines of all of your various ranks might not all be at the same line of code at a given point in time. In fact, that's kind of the point of a parallel program. So if you're looking at CPU codes and you do a list, it will print out 10 lines of code for each rank that's not in the same location, right? So you might get a lot of output, especially if you're running at a high scale. And we've used Gdb4hpc. You can use it up to and beyond 1,000 MPI ranks. Of course, you have to have a large enough system to support 1,000 ranks, but it scales up at least that high. So they've tested it for that reason, but you're going to get a lot of output. So it might be useful to have, if you're just looking at the code to have it, you might want a second window with your code open. So you're like, oh, it tells me I'm at line 35. This is what's on line 35. It might be good to have. Maybe even a loop mark listing. Okay, step, pretty straightforward. You go advance one line. And so that's, useful. And if your code calls a function, step will step into that function. So you're kind of just going exactly along with the program counter and seeing what the next instruction is. If you do next, that will skip over subroutine calls, right? So sometimes you're like, I know what this function does. I don't need to debug it. I'm just going to do next. With step, and I believe with next, you can do something like S, shorthand, because the extra typing is for suckers and guys like me. Or you can do step and a number, right? So step 5 will take 5 steps. And so that is, you can increase your productivity. So although be careful, right? You might step over your problem. And you won't step over it, you'll step into it and then past it. So, these just kind of, it takes a little practice. If you want to see a variable, and if you haven't ever done a lot of interactive debugging, this is the value, right? Where you're looking at lines of code, and then at a given point in time, you're saying, what is this variable now? And then, later, what is it later? And inevitably, that's the problem, right? You're looking at a variable and saying, I'm expecting it to be this, but because I've made a mistake and the code is behaving differently than I expect, my variables actually got a different value than I expect. But being able to see that will allow you to be like, oh, recognize the problem and then make a change, right? So printing, stepping, super useful, and we're going to be doing that. We don't want to talk about continue until we've set a breakpoint. So with our code, obviously a lot of codes are quite long. You can set a breakpoint, which basically says, no matter what, stop here, right? So a breakpoint can be at a line number, it can be at a function name, and there may even be other choices. Some compilers allow for a logical breakpoint, like break when a logical condition is met. I don't know how to do that in Gdb4hpc, and I'm not actually sure whether it's supported. But certainly line numbers and functions you can do, right? So you specify a breakpoint, and once you've specified a breakpoint, you can see the breakpoints that you have, and you can continue, which basically says run at near normal execution speed until you get to the breakpoint. So that's what we want there. If you if you have a breakpoint inside of a loop, you might continue, and then you'll just, okay, cool, now I'm at that breakpoint again, the next iteration through the loop. And if you recall the loop mark listing we looked at a little while ago, we were passing through a loop 6 million times, right? So you might not want to, do that every time. So you can disable a breakpoint and basically say, from this point forward, don't stop at that point, keep going. But and then you can enable, and there's some options like enable once and things like that to have some granular control over your breakpoints. So once you're stepping and printing, the next thing that you want to do is set breakpoints, continue to them. These will allow you to kind of somewhat quickly navigate around your application. Okay, so For GPU specific stuff, and not just GPU, but CUDA specific stuff, there are some CUDA specific commands that we have access to. So there's a CUDA help info, and that's a little bit just like the regular help. It'll show you specific things you can do with CUDA. And there's also info CUDA threads. And I have a printout of this later. This shows you basically info or information on the running threads. And even in a simple application, this generates a lot of output. And so there's kind of a lot to take in. And I think you need to have some practice to really make good use of this. You can see and or change the block that you're focusing on, and also the thread, right? And not just those. There are similar things to block and thread. I think with device and grid and some things like that. Warp is a command where you can see the warp that's going on. And so again, just I find the GPUs are very powerful. They give you this capability to do things in massively parallel things. But like my brain, at least in the way I perceive it, is not parallel. It's quite serial. And so, or at least with respect to my ability to comprehend what's going on. So sometimes it takes a little bit of practice to really dig into the debugger and be like, all right, I'm seeing it, but in this GPU code, there's a lot going on, and it's a little bit tricky to see all the pieces. So we have an opportunity for you to dig into that. And because Gdb4hpc is extending the CUDA debugger for purposes of CUDA codes, you can refer to the NVIDIA documentation on the CUDA debugger for some additional information like this. So basically, it sits over top of our debugger. So you, while you're using our debugger, you can reference these commands and they will work more or less the way they would if you were calling this natively. So, but you can call it from an MPI program and see all the ranks and threads, and it's kind of neat. So, printing variables has a couple of unique syntactical things, and so we wanted to provide some details on that. So if when you with MPI in general, you have, let's say in this case, we have 8 ranks, but if you have some number of ranks, each of those ranks will have its own memory footprint, right? Meaning so that all the variables that you've declared in your program will be duplicated for each of the ranks that you have. And they might be on the same node, they might be on different nodes, but they're all gonna potentially have distinct values. So when you print out a variable, you need to recognize that you're asking about the value of as many variables as you have ranks, potentially. So, and they could, of course, all have different values at a given time. So that's kind of the point of parallelization, right? So here, if you just print out the name of a variable, you might get one line of output for every rank that you have. And this is what that would look like. One of the things that we do with MPI is we pay attention to which rank we are. So we would actually expect COM rank, excuse me, we would expect COM rank to have a distinct value in each rank, and clearly it does. That's a good thing for us, but it makes a nice example, right? Another thing that we do with MPI is we look at the size of our world, and a variable that's typically available within an MPI kernel is size, and the variable actual names might vary. They're declared, and then you populate those with an MPI function call. But in this particular program, we use something called COM size. And for all 8 ranks, it is the same value. That again is expected, but that's a good thing. And this gives us a chance to see when the variables are distinct, we get one line per distinct value. When they are the same, we get a line indicating that it's the same value in all 8 ranks. If you want to look at just an individual rank, to do that, you need to remember the name of your application, or that you've given to Gdb4hpc. And then with curly brackets, you specify the rank, and then we have the double colon and then the variable. And the $sign is not optional. So it's easy to get this wrong, but this way you can kind of print out variables from a single rank if that's what you want to do. And then the last thing that I thought was kind of interesting is if you want to print a values from an array. So here I'm looking at an array called input. I'm starting at index value 0, and I'm saying at 8. So give me the 8 values. Now, how big is the array? Well, it's at least 8 values long. I guess we don't know just from this shot. But I'm looking at the first 8 values from the array for each rank, because again, the memory footprint is per rank. They could be distinct, and it looks like in this case they are. So that's good. Okay, so printing variables, very important. A couple of syntactical gotchas there. Hopefully that makes sense. So if you are debugging a parallel application, you might want to actually only look at a single rank or a subset of ranks at one time. So Gdb4hpc has some commands that allow you to focus on a particular rank. And this application is an application I've used in previous trainings. It's a little toy code I wrote to calculate pi, but it's an MPI application. So this doesn't look like the other things, but it works, okay? Trust me. So here I have launched my application, and it's running on 6 ranks, okay? So that's what we can see that. If you focus on a particular rank with this syntax, the keyword is focus, and then your handle, and then provide a range. Here I'm providing just a single rank. Our prompt changes and our output changes, right? So if we can run commands, we can step, we can continue, we can next, we can do whatever, and whatever we're doing with our interactive debugger is only going to apply to our focus, right? So now I've stepped, I'm at line 26. I've stepped again. Now I'm at line 27 and 29. Presumably there was nothing going on line 28. And then I do a focus all. And when I do a focus all, it brings me back, kind of steps back from my focus, right? And if you do a command, the frame command, that will show you where you are in each of your ranks. And so what you can see is rank 0 is at line 29. Ranks 1 through 5 are at line 25. So you can kind of move in and out of individual MPI ranks or subsets of ranks and kind of just explore what they are doing while the rest of the program is paused. This is a cool capability. It's useful. But at the same time, it allows you to run your program in a way that your program wasn't intended to run, right? In theory, all your ranks are running, in parallel, right? That's the kind of the whole point. So if you, I have definitely had parallel applications that I have tried to debug with Gdb4hpc. And if you set like a breakpoint, for example, in a loop, and then you can't get out of that, you can get yourself into trouble with GDB by basically breaking how the program runs and not letting it it basically gets stuck. You can set up like a race condition or things like that. That won't actually happen when you're running the program outside of a debugger, but it's something that you can run into. So cool feature to be aware of. Definitely give it a try, but also be careful of how you're running your application and whether you're doing something that won't actually happen as you're running it live. So finally, we have a view of info CUDA threads. This is one of the commands we can specifically look at our GPU behavior while we're running. So here we are inside of our CUDA application, and this is showing a block ID, thread ID, how many threads we have at a particular location. And then we can see also the source code and also the line number. And when you're looking at GPU codes with dramatic fan out of parallelization, it's often the case that all of your threads will not be at the same location, right? And so that's remember that a step with respect to CUDA is at the warp level, right? So when you do a step, 32 threads are all going to advance, and there's no way of separating out that to be at the individual thread level, because that's not how GPUs work, right? The GPU does, one thing, 32 copies of one thing at the same time, and that's kind of as granular as the GPU can get. So that behavior, again, is just a little bit, takes a little getting used to, but this will give you some insight as to what's going on. And so, and we can see, again, this is the output is showing you the perspective of each MPI rank. So each MPI rank will have its own potentially set of GPU interactions, right? So you have your own set of threads and blocks and all that, because the what's going on in the GPU is in scope below what's going on at the MPI rank. So we've got a lot of layers here. There's a lot to unpack. The asterisk is indicating which GPU rank has the current focus. And so if you do a command in the GPU debugger, it's going to apply to the thread specifically that is being called out by this command. And if you do something like a CUDA block, like I could go to CUDA block 649, and instead of focusing on CUDA block 0, and now I'll be focusing on block 649, right? So what you're doing with that, you kind of, again, you have to understand what the program is doing and understand, why there is a block 649 and all that. So that's goes a little bit deeper than this presentation goes. But if you are able to navigate, that's my objective, is to give you that information on how to navigate. So there we are. It's enough of me talking. It's time for you all to give it a try. So we have our last hands-on activity that is going to allow you to run Gdb4hpc with this simple MPI program. And it's, again, you will want to work out of scratch, although you'll be creating an allocation. And so, that follow the instructions. Helen, is there anything that you would like to add, or anyone else, before we move into lab exercises?
Yeah, thank you so much for the presentation. Lots of detailed explanations. So before the exercises, I do see 2 questions in the Q&A doc. That's good for you to answer. And those are, as part of the recording.
Sure.
Are you
Okay.
able to access Q&A, or should I read them to you?
I'm looking, my screen is not that where the camera is,
Okay.
so I'm reading them. Okay, so there is a question from Sam Young on slide 60. Is that
Yes,
okay? So
we're using Slurm arguments in GDB.
why are we using smart launcher args inside the GDB? I don't see where GDB. Okay. If GDB
Let's
for
read the
HP,
questions, so that's recorded.
yes, I'm sorry. Okay. On slide 60, so let me actually back up to slide 60 for people to see that. One more. Oh, too far. Sorry, too much going on. Too many screens. Stay. Okay. On slide 60, we are, why are we using swarm arguments minus capital N 8 minus C32? I don't think I think that's a typo. It should be minus lowercase n 8. Yeah, in launcher args inside the Gdb4hpc debugging session, I don't see anywhere where Gdb4hpc is calling srun. If Gdb4hpc is calling srun as the launcher, is there an option to change which launcher is used? For example, if we wanted to profile non-MPI programs. And so my answer is that Gdb4hpc is launching the application, and whether it's actually calling srun or it's using a API that is made available by Slurm, I'm not totally sure, but it's effectively how it's mechanically implemented. It is effectively, you can think of it as being the same as it's calling srun. And so that launcher arguments that we're specifying. So minus capital N2, which indicates distribute these ranks over exactly 2 nodes, minus lowercase c32, so allocate 32 CPU cores, again, logical cores, to each rank, and minus minus GPUs, which is ensure that this job has access to 8 GPUs. Those arguments are arguments that Gdb4hpc doesn't, they just blindly pass those to the underlying application launcher, which in this case is Slurm. The 2 workload managers that HPE systems work with the most are Slurm and PBS Pro. Historically, we have worked with others, but those are the primarily supported workload managers. And in both cases, if you're launching your application with a debugger, of course, they would have distinct syntax in the launcher arguments. And in both cases, Gdb4hpc will take launcher arguments, again, exactly as you would feed to the launcher, and it will just pass those to the launcher that it calls under the covers, which is either srun or I think it's actually like a some kind of Slurm API that functions like srun. So hopefully, Sam, that answers your question. And if you wanted to profile non-MPI programs, the way I do that is to do an srun minus n1, which, by the way, is default, right? By my lowercase n1. If you don't specify, that's what you get. And running a MPI program on a single rank is sort of similar to running a non-MPI program. If you don't call, the MPI functions and don't have them even linked in, you can still launch them with srun. It does work, and that's what I've typically done. If I'm misunderstanding the question, I would invite my friends at NERSC to fill me in. Or I know there are things like MPI run that you can use elsewhere, but on the systems that we sell, pretty much just always use srun, whether it's MPI or not. Anything to add to that, Helen?
I think you pretty much answered very well.
Okay,
Yes,
thank you.
that's wrong. If using MPI ROM probably needs some other, when we have another MPI loaded, then even those we also have SROM wrappers for those usually.
Right. So I'm aware of it from other systems, but I've only ever used srun, and PBS Pro is a different animal, and so there's obviously not srun, but we have a specific to our programming environment. We have something called PALS, which is the Parallel Application Launch Scheduler, I believe, but not applicable at NERSC. Not, so I don't want to confuse anybody, but it's a launcher, right? So we have our own launcher. Not important here. So the other question is, I'm going to mispronounce this name, Junkao or Jun.
Yes. Yes.
Okay, apologies on the pronunciation. So can we set breakpoints inside CUDA kernels in Gdb4hpc? The short answer is yes. And the command to do so, we actually have you do that in the lab. I will again confess, CUDA applications are a little bit more complicated than my feeble mind can fully comprehend at times. But absolutely, yes, you just break, and then the function name is what we did in the lab. I think it's possible to specify a line number as well. While you're working on the lab, I will check. I've got some resources I can look at, and I'll provide some additional comments in the Google document to provide the syntax for how you could point to a particular line number within a CUDA kernel. But absolutely, yes, you can do that, and you'll be doing that in the lab exercises if you follow the instructions, or someone's already providing an answer. So I'll review that, but it looks good. So I think that was that. Or maybe so that's, I'll provide some additional detail to that question, but short answer is yes. So I don't see any other questions before we go to the lab exercises. Are there any other questions?
Yes, I have a quick question.
Please.
Right on that slide, 63.
Okay. Oh, sorry. Okay. Yes.
So the syntax for printing an array, is that GDB syntax, or it's, let's say I have a Fortran code. Is that going to be exactly the same syntax?
Ooh, excellent question. You know, I need to check on that. So in fact, this code, this example was taken from the code that we're going to use in the lab, and so I don't do programming every day. The array is passed to the kernel as I recognize it as like a pointer, right? Which is, maybe that's normal, but my programs are simpler. So whether it's defined as an array in the host and then passed as a pointer, or some other thing, I would need to look further. And then how it works in Fortran,